In this video, we'll show a conceptual centrifugal compressor design with CFturbo, the application for the refrigerant R134a. We explain an automated optimization workflow with Ansys workbench, and we will present some simulation results. First, we create a new project choosing the compressor design module. In the global setup window, we specify the design point of the compressor. CFturbo aims to reach the best efficiency point, or the BEP, for the design point. The design point, or duty point, is defined by mass flow rate, total pressure difference, or total pressure ratio, and rotational speed. In this case, the fluid is R134a. Additionally, we have to set inlet pressure and temperature. Besides the ideal gas model, different real gas models are available. The integral part of the CFturbo software is the CoolProp database containing fluid properties of numerous gases, liquids, and mixtures. On the right side of the window, you'll see the general machine type based on its specific speed, as shown in the Cordier diagram. Next, we add a new component, choosing the radial mixed flow impeller option. In this example, we will make an unshrouded, single-stage radial compressor. In the setup window for the main impeller dimensions, we have to set the tip clearance between the blade tip and casing, and we must decide if we want to use splitter blades. In the parameters section, we can select empirical function to design reasonable impeller main dimensions from the very beginning. In this example, we use correlations for work coefficient, diameter ratio, and meridional deceleration. An estimate for the efficiency is required as well. The empirical correlations in CFturbo are taken from textbooks and research papers, or are based on our data. Most of them are accessible and adjustable by the user. This gives a unique possibility to customize the code for their own applications and to maintain proprietary information. Our software will provide a reasonable design proposal for the main dimensions, such as shaft diameter, suction diameter, impeller diameter, and outlet width. On the right side of the window, we can see the essential physical values, an initial sketch of the meridional view, the impeller within the Cordier diagram. The user can modify all geometrical values manually. It is an available option throughout every design step of CFturbo. Here we have used the automated option to create an initial impeller design automatically. In the 3D viewer, we get an impression of the geometry of the model. In the meridional contour design window, modifications of hub and shroud contours can be made, as well as shaping repositioning of the leading and trailing edges. On the right side of the window, there is a 3D CAD preview and an area progression diagram of the meridional flow channel. Other options to support a user shaping the impeller's meridional contours are static moment and curvature, among others. As shown here, we adjust the leading edges of the primary blade and splitter blade. The blade edge projections can be straight lines or Bezier splines. There is high flexibility to modify the shape of the hub and shroud by moving Bezier points interactively. After modifying the hub and shroud separately, each geometrical modification is shown directly in the diagrams. An additional design method is available in CFturbo, where you can manipulate the middle section of the meridional contour instead of hub and shroud. Now we create the hub solids. The CFturbo software is very flexible, in general, for modeling solid parts of geometry. For example, we can split the curves or transform them into Bezier splines. Bezier points can be added or removed without limitations. For demonstration purposes, here we're creating a simple model of the hub contour. If applicable, the description of hub and shroud contours can be part of the secondary flow path design. And we can set the impeller's axial length as shown here. All Bezier points can be modified numerically by changing numbers in the pop-up window. Later, hub solids and blades can be exported directly into any CAD system or meshing tool for structural or thermal analysis. The next impeller design step is about blade properties. It mainly comprises the calculation of blade angles at leading and trailing edges of main blades and splitter blades. Several options for slip factor correlations are supporting this design step. At first, we set the number of blades and the number of spans. Then we choose a blade type for our application. In most cases, this selection is determined by the manufacturing method of the impeller. Then we initially define blade thickness on leading and on trailing edges. With this and a slip factor correlation, we can calculate the blade angle on every span. On the right side of the window, we see from left to right velocity triangles, two tables with all velocity components and blade angle values at leading and trailing edges, a meridional sketch, and a diagram that explains the slip factor calculation. For the blade mean-line design, CFturbo offers various possibilities to create the fundamental blade shape. It is mainly all about calculating the blade curvature on every span between leading and trailing edges. Since this example should be designed with ruled surfaces, which are preferred for flank milling, we only have to work with two spans, hub and shroud. For the ruled surface, there will be a linear interpolation between hub and shroud. The blade angles of leading and trailing edges are fixed in this design step. There are graphical and numerical possibilities to modify the wrap angle of the blade, which has a strong influence on the blade angle distribution. Likewise, there are graphic and numerical options to adjust the curvature of different spans. The Bezier curves can be modified by drag and drop or by writing numbers in checkboxes of Bezier points. On the right side of the window, there are options to configure various diagrams and geometrical views to evaluate the blade design. Blade-to-blade calculations and blade surface calculations are based on the Stanitz-Prien methodology. Among others, we can select estimates of Mach number, absolute and relative velocities, pressure, swirl, and blade loading. A real-time 3D view of the blade directly shows the modifications in three-dimensional CAD. In general, the user can choose between direct beta distribution, M-theta conformal mapping, or inverse design by blade loading for centrifugal compressors. The next design step, blade profile design, is mainly defining the blade thickness distribution. There is high flexibility in CFturbo to do this. The user has options for linear or freeform shapes. The suction side and the pressure side of the blades can be made symmetric or non-symmetric. You can work with different profiles on every span if necessary. For high performance or high efficiency requirements, a user can import predefined profiles like NACA or their own point-based data. On the right side of the window, the user has options to see blade-to-blade calculations or blade surface calculations as in the previous design step. The 3D view of the blade profile directly shows the model in three-dimensional CAD. On the right side of the window, the user can configure the same view options as in the previous design step: area, progression, Mach number, Relative and absolute velocities, swirl, blade loading, etc. are available. The 3D modeling of the blade edges can be seen in real-time modifications. In this example, we have used an elliptic shape with an axis ratio of 3 for the leading edge design, which is typical for those types of blades. If we would set the axis ratio to 1, the leading edge becomes an arc, as shown here. For the trailing edge, we use the simple option. The user has the possibility to trim the blade on the outer diameter of the impeller. But for the trailing edges, too, you can use curved shapes like elliptic or Bezier. Before we proceed, we save the CFturbo file. Now the basic design of the impeller has been finished. We can see a section of the model in the main Meridian window of CFturbo. We also can show the impeller geometry in our 3D viewer. CFturbo's volute modeling is fully parametric and versatile. In the first volute design step, we specify the inlet data for the volute. Fluid dynamic and thermodynamic numbers will be transferred automatically from the upstream component, as shown on the right side. Like in every other design step, the inlet geometry settings can be adjusted manually by the user. In the next volute design step, we select the cross-section shapes. There are different options to shape the volute. From rectangular over round, line segments to Bezier and radius-based profiles are possible, symmetric and asymmetric. And cross-section shapes may vary in the circumferential direction. Here we've chosen a round asymmetric model with a strictly external shape. The heart of the volute design module is the spiral area calculation. It is based on Fleiderer or Stepanov's theory. A user can select the constant swirl or constant circumferential velocity approach. Alternatively, CFturbo offers the capability to set an area progression defined by the user. Together with our cross-section area options, this allows high flexibility in volute design. On the right side, you can select and configure diagrams and view options to support the design process visually. At any time, the 3D viewer of the full model can be used to check the geometry. The next volute component will be the discharge diffuser. The discharge diffuser is usually necessary to connect the volute itself with a piping system. It is a critical component, both for aerodynamic and aeroacoustic reasons. The volute and its discharge diffuser have to fit perfectly into the impeller. We can modify the length, the outlet diameter of the diffuser, and its outlet cross-section. The initial created tangential diffuser can be made with end-centric or with non-centric outlets. Besides tangential outlet directions, there are options to make radial or spline-based shaped discharge diffusers. Another kind of flexibility is given by a Z-bend option. The cutwater or tongue connects the spiral casing to the discharge diffuser. The tongue's design is challenging, too, because of aerodynamic, aeroacoustic, and structural requirements and manufacturing constraints. For the tongue design, there are currently 3 design options in CFturbo: simple, fillet, and sharp. Here we create a fillet, replacing the initial simple cutwater design. We can modify the radius and the spiral start position. Here we modify a 1 mm radius. The shape of the cutwater will be automatically updated in our 3D viewer on the lower right side. Above, we see a table with essential geometrical data describing the tongue. Next, we see the full model with impeller, radial diffuser, and volute in the 3D viewer of CFturbo. Now we take steps to prepare the CFD model. At first, we add an outlet extension downstream of the discharge diffuser. For numerical reasons, the pipe should have an appropriate length to prevent an impact from the boundary conditions to the compressor stage itself. Here we have added a 300 mm outlet pipe about 3 times the diffuser outlet diameter. Second, we have to close the gap between the impeller's outer diameter and the radial diffuser's inlet. To do this, we go to the CFD setup menu of the impeller. We have to mark the RSI outlet checkbox on the right side. RSI stands for rotor-stator interface connection. As an alternative to the CFD setup's RSI connection, a user could define explicitly placed a small stator between impeller and radial diffuser. To finalize our compressor stage and prepare the CFD simulation model, we add a pipe on the impeller's suction side. Likewise, for numerical reasons, the inlet pipe should have an appropriate length to minimize the inlet boundary's impact on the compressor impeller. In this specific case, we add an inlet extension of 100 mm. For the actual model, as shown, we design a hub nose. At first, we have to modify the main dimension of the inlet. Then, we split the lower curve into 2 sections. One part is representing the axis, and the second part will describe the hub nose contour. The hub nose can become a simple circular area, a cone, or it can get a free-form contour made of 1 or more Bezier splines. A combination of Bezier splines and straight lines would be possible too. In this model, we use the latter. In CFturbo, the modeling of rotational curves and surfaces is versatile and flexible. The exact positions of each Bezier point can be set or modified numerically. We check the geometry in the 3D viewer of CFturbo, and we change the color of the hub nose. The user should be aware of specifying this part as a rotating wall in their CFD setup. Adding inflow components upstream and outflow components downstream of the compressor stage completes the computational domain already in CFturbo. Such a possibility is helpful, especially to set up for automated design space exploration and optimization. Before exporting the model, we make a model finishing for the impeller. Model finishing is an operation to create high-quality solid models of selected components. Model finishing is required for some export interfaces, but not for all. And in this design step, there is an option to specify fillets between blade and hub. In our example, we set a 0.5 mm fillet radius connecting the impeller hub with the main and splitter blades. Considering the fillets is essential, especially for structural modeling, but also for flow analysis if the dimension of the impeller is small compared to the fillets. As shown, CFturbo has export options to all significant CFD codes and CAD systems, and neutral formats like STEP, STL, or Parasolid. Interface development is a crucial part of the CFturbo development strategy. It is the basis for parametric design exploration and automated optimization. This example is exported to CFturbo MP, also known as Cimerix MP. Cimerix MP is a modern, robust, fast, accurate, and cost-effective general-purpose 3D Navier-Stokes solver. Correctly done, 3D CFD simulations can provide realistic predictions that compare accurately with experimental investigations. This slide gives an actual overview of important CFturbo export interfaces to CFD selected codes. The list will be continuously extended. Besides direct interface, there are numerous neutral export formats available, like STEP, Parasolid, or STL. There is a fully bidirectional integration of CFturbo into Ansys Workbench available. The parametric modeling of CFturbo can be addressed for meshing, simulation, design exploration, and optimization. Through its bidirectional integration of CFturbo into Ansys Workbench, there is a truly seamless, highly productive way to work with CFturbo and Ansys products like TurboGrid, CFX, or Ansys Mechanical. It offers interactive or automated design optimization. To set up the optimization process, one has to define the optimization objectives, select the variable geometry parameters and constraints. In total, we choose 8 parameters of impeller and volute to achieve a high stage efficiency. The pressure ratio, total static, of the compressor stage has to be in a specified range. The optimization. We use a mixed integer sequential quadratic programming MISQP, has produced 141 valid compressor designs. 2 of them were excellent proposals with high stage efficiency over a wide operating range. In this slide, we visually compare the impeller of basic design 2 with optimized design 107. The performance maps show data of a wide operation range. For this example, the speed varies from 30,000 to 44,000 RPM. The stage efficiency, total to static, is beyond 70% in the main operating range. That's excellent for a small size compressor. The total project time was 10 days, including 2 manual design loops and the automated optimization. The process was run on a modern 12-core workstation. With more computational resources, the process can be accelerated substantially. CFturbo and Ansys Workbench is a user-friendly, straightforward tool for centrifugal compressor design. To register for a free trial and to learn more about our engineering services, please visit cfturbo.com.